Okay, YouTube, this is my fifth video on solving trig equations in which we are going to just run through another example. In this particular example, we see we have a secant squared x minus tangent x equals 1, and we have trig functions of two different types here. So the first thing I'd like to do at least is if I'm going to solve this and I have two different trig function types, I'm going to try to factor it as much as possible. So I'll set this equal to 0. So we have on the left side here secant squared of x minus the tangent of x. And if we were to subtract the 1 over to this side, we have minus 1 equaling 0. Okay, so now we have this equation right here. And I noticed that it's a little bit difficult to factor given that they don't have any common factors. So what we're going to do is we're going to try to make this all of one trig function type, if at all possible, using trig substitutions. Now, I realize that tangent of x is also sine of x over cosine of x, but that's not very helpful here in the grand scheme of things. We could work eliminating a denominator into a lot of algebra, or we could say that secant squared of x here, we can make a Pythagorean substitution because we know that secant squareds and tangent squareds go together very well with Pythagorean substitution. So our basic Pythagorean identity says that the sine squared plus cosine squared of an angle equals 1. So if I wanted to build this with, say, secants and tangents, then I could say, well, what if we took everything and we divided it by a cosine squared? Divide by cosine squared here. That would give us a secant squared, cosine squared here, cosine squared here. And what we end up with is this new trig identity. It's still Pythagorean. We'd say, well, we get secant squared x, which we're going to make a substitution for the secant squared x. But I notice that this gives me a tangent squared x plus 1. And if we were to substitute this value in for this right here, then we would see something that is in all of terms of tangents. Okay, so let's go ahead and make this substitution here. This minus the tangent of x minus 1 equals 0, where we have a substitution of, instead of secant squared, we have tangent squared x plus 1. And I'm going to clean this up a little bit here. It doesn't seem that we need the parentheses here. I don't have any negatives in front. And this positive 1 and this negative 1 in the back, actually, as a matter of fact, this is a wonderful thing. They just kind of combine like terms and cancel each other out. So now we're left with this. We say tangent squared of x minus the tangent of x equals 0. And in terms of factoring this is a piece of cake. These two terms have a tangent, a single tangent in common. So we say tangent x being factored out front. We're left with tan x minus 1 on the inside equaling 0. And so now we can say, well, this times this equals 0. Let's set each individual factor equal to 0 and solve these. So we have the tangent of x equals 0 or the tangent of x minus 1 equaling 0. And I'm going to go ahead and start by isolating this tangent on the right here. We say, well, then the tangent of x equals positive 1. Okay. So now let's undo these trig functions using inverse trig functions here. We say tan inverse of both sides of this equation. I'm going to do the same thing over here. We have tan inverse in this particular case. It's kind of cool. And so these cancel out, and we're left with all possible solutions as being the solutions that satisfy this statement here. Angles that when you took the tangent of them, you got an angle of 0, or an output of 0, and also angles that when you took the tangent of them, you got an output of a positive 1. So we need to stop and ask ourselves a few questions here, starting with this. What were the reference angles then that we're dealing with if we got these for answers? So we say, where is tangent equal to 0? Well, first of all, I mean, we wouldn't even need a reference angle for this one. If we had the unit circle of radius 1 here, we say if tangent came out to be 0, then when we took y divided by x, we got 0. So what points would this have to be at? Well, it'd have to be at 0 radians here. And it'd also have to be at 180 degrees or pi radians because this is negative 1, 0. So we'd say that this has a, you could call it a 0 radian reference angle. And even if you went back and sketched it, we could say, well, 0 is here and here. So we'd say 0 radians and pi radians. But this allows us to find the two solutions here. We say x is equal to 0 radians plus pi n. I added on the period of tangent, multiples of that. We say x must also equal pi plus pi n radians. These are all possible solutions to this equation right here. And likewise over here, when we say, well, what's the reference angle if tangent came out to be 1? Well, I know this. We say that it must have been a pi-4th radian reference angle. So since this came out to be a positive 1, this is an instance where I do actually have to go through and say, well, we're going to have to go sketch the reference angles in. But I know that since tangent came out to be a positive 1 here, that it must have been hanging out either in the first quadrant or the third quadrant. So we say, here's my pi-4th radian reference angle here, and here's my let me try to draw this a little bit more cleanly. Here's my pi-4th radian reference angle there. So we say these two angles must be pi-4ths in standard position and 5 pi-4ths. So we say that x, I'll try to be consistent here, is pi-4ths. This is a tangent function, so add on the period of tangent multiples. And then we say x must also be 5 pi-4ths. plus pi n. And again, we could verify this on the unit circle. We say, just looking at your unit circle, we say, where did tangent come out to be 0? That's what we were asking here. And there are two locations. Tangent comes out to be 0 at 0 and pi radians. And we say, where does tangent come out to be a positive 1? It'd have to be at a positive pi force here and a positive 5 pi force here, because root 2 over 2 divided by root 2 over 2, or sine over cosine in those locations, would give you 1, positive 1 in either case. And so the last thing I want to do, last but not least, is this. I would like to verify this graphically. So I did go graph secant squared x minus tan x minus 1, where I've already set this equal to 0, but we can see that 0 and pi were the first two solutions to the first equation there, and then pi force and 5 pi force. And you notice that if we were to add pi onto 0, you get to pi. Add pi onto this, you get to 2 pi. I add pi onto this and get to 3 pi. So that's why we were adding on multiples of pi to each of these original solution values that fell between 0 and 2 pi. Cheers.